Hi, and welcome back. Last time we had generated the equation from our four fundamental forces with the aircraft in a climb to kind of take a look at how an aircraft is starting to be configured in a trade space, right? And we've talked about this kind of curve and the feasibility, and we generated that equation that starts driving some of these curves. However, we had these left open terms that needed some more definition. As in, what is the dynamic pressure that we're flying at? That's a combination of speed and altitude. So what is that? What is the thrust lapse rate? This is alpha, right? How is that falling off compared to the thrust of the engine at sea level? Or is it going up? And then we also had then the weight of the vehicle. At what range of weights are we talking about? And certainly in the flight of a system, you would need to be considering both, say, a takeoff, that might be this curve here, but in a curve that might show up on cruise, then it's, well, is it cruising early? Is it cruising late? And then all of this is then not quite complete enough to then drive down to what we're actually chasing, which is range and speed. But I wanted to take this episode to really first get into the dynamic pressure. What is the speed and altitude? We've talked about it a little bit before at a high level. This time we're going deep in. Because ultimately, as a high-speed vehicle, the temperature is setting where you're flying. And so that is, that velocity is really going to be set by the temperature. And that from that temperature is going to give you the altitude that you want to fly at, as well as that dynamic pressure Q. And a reminder, the dynamic pressure is 1/2 rho v squared, and the densities is coming from the altitude. Okay, so looking at a force balance on the vehicle and just looking at the friction forces, right? This would be the force due to drag friction times velocity. That's generating the power. That's the friction power. Some portion of that turns into heat, and that is going to come to the system, and that we would then have to reject. The assumption at this point is that your vehicle is hot. You've got no more ability to absorb that heat. You have to reject all of it with radiation. Now, if your flights are really, really short, like 2 minutes, 3 minutes, this is not true. Certainly, any aircraft, flying for 45 minutes at Mach 4 or, a couple hours at Mach 4, it's going to be true. And so we really need to then design for the system where this fraction of this power, right, is going to be rejected by radiation. And so I'll just say right here, there's some fraction, CF, CH, will come back and define, but that all has to be rejected. And so it's an emissivity of the surface, right? Nothing is a perfect emitter. And in fact, nothing's perfectly emitting at all frequencies, but we'll just at least put a number from here for now. There's the Stefan-Boltzmann constant, and then radiation is T to the 4th, and this is comparing it to T infinity would be the atmosphere way out there where you're rejecting to. That's why I remember when we talked about the temperature inside of the engines, you don't have an infinity here to reject to. So all of that hot air coming inside of an engine, you have to cool that or be able to handle the temperature that it's at. Okay, and so really this comes from what is the friction. In fact, that friction is just going to be shear stress, okay? And so what we need to do is find the formula for friction. So it'll be 1/2 rho v squared. That's kind of that dynamic pressure standard again. And then CF, this is the coefficient of friction, and then it's times S. And I believe I need an S here as well. And I'll just say an S there for surface area in general. I know we've talked about S being just the wing area in the past. In this current formula, this would be representing the full system. All right. Flow over, we'll draw it here. So flow over a flat plate develops a boundary layer, and that boundary layer, normally you draw like this, the boundary layer will grow. And so what you're actually seeing here is that up top you have some free stream velocity, also normally called V infinity. And at some point, that velocity then comes down to 0 at the wall. So there's some shape there. And you can define how, you can get into different definitions of what is the boundary layer height, but that's usually how it goes. And then at some point, this boundary layer starts to become very unsteady. This is then turbulent. So this is turbulent boundary layer. And back here is laminar. Now this transition happens Normally a Reynolds number, the Reynolds number is the density, the velocity, position x down this length over the viscosity. And this turbulent transition happens usually when this is around 5 times 10 to the 5, although in compressive systems, there's been some research papers out there saying this could hit even 1 times 10 to the 7. That's a big variation. And so a lot of this will depend on the configuration of the aircraft. You certainly can transition and trip to turbulent before you're wanting to, and it can be challenging to try and stay laminar if you're looking to stay laminar. So even within this, there's a fairly big jump that can happen in terms of your heating. Okay, and so then the skin friction, if you're laminar, I'm going to toss some room here so it's not confusing. If you're laminar, okay, the CF is 1.328 over that square root of Reynolds number. And then if you're turbulent, the CF is 0.074 Reynolds to the 1/5. So first thing you have to do is figure out where are you at. Are you laminar or turbulent? And I mentioned it here, it is important. You're going to see in the end that we're going to end up flying higher. And this laminar turbulent transition is actually going to be right in the noise, right where that vehicle is going to want to fly. And so this is important here to write it down, because you may end up wanting to design wings that are mostly laminar at those speeds and altitudes to take advantage of some heating. Maybe that gives you a little bit of material relief on the wings. Maybe the body is going to be fully turbulent. There's no way around that. So maybe the body, you eventually have to hit that, right? And so I mentioned it here because it's become super important. And then this CH to CF, this is the ratio of how much of this friction is actually turning into heat. There's a decent model for this, 1/2 times the Prandtl number to the 2/3. And if you haven't heard of what the Prandtl number is, it is simply alpha over nu, and I warned you there's going to be more alphas. This alpha is actually thermal diffusion, and the nu here is viscous diffusion rate. It's kinetic viscosity. Okay, so a bunch of equations there. I'm going to finish ultimately with just this one equation, which is that T on the wing surface, the body surface in general, right? This is kind of a 1D system, is 1/2 the ratio of how much is heating, CF rho phi cubed. You do get to divide by the emissivity, so paint it black if you can, or make sure it's very shiny. Stephan-Boltzmann's constant. And then, of course, you do pick up this T infinity to the 4th. When we get really hot, this is in the noise. All of that to the 1/4. So you end up having velocity to the 3/4 if you catch that. And then you do pick up some density term in CF. So this is ultimately the temperature. And that's the part that's going to come in and really set, right, what is the density here based on the speed you're trying to fly at? It's going to be set by what is the maximum temperature that you want to hit. Okay, and so it ends up looking like this. Now I did a couple of plots. This is dynamic pressure in pounds per square foot. And let's say you want to fly at 800. That's a good number. So maybe it's 1,000. Some vehicles might have a higher number that, at some point you'd have sort of structurally, that's kind of your structural stress on the vehicle. So maybe you want to fly at 800. But if you have a 100-foot aircraft, those are kind of the curves in grayscale. That becomes the velocity that you have to start rolling off. And so if you have 900 Fahrenheit, let's say that's titanium, you can quickly see here how that dynamic pressure is going to drop down. In fact, at Mach 4, you might be only at like 100. Mach 3 might be like 180. And so that 100-foot aircraft is going to be challenging if indeed you're trying to stay at that 900. Now, if we at Venus, we think this is potentially doable, but this is the reason we're worried about that number. Now, wings, I put here, say, a 30-foot wing. That's the blue curve, right? Maybe this is doable. Maybe at Mach 3, Mach 4, that's enough dynamic pressure that's doable. Or maybe you could see some combination here. So the next kind of darker gray would be at 1200 Fahrenheit. So maybe, that would be, say, a stainless steel. Or maybe you're a little bit more comfortable with some of the blends of titanium. If you can get to 1200 Fahrenheit, maybe you're able to fly Mach 4 almost at 200 feet on the entire vehicle. Or Mach 3, you might come back and be at 300 pounds per square foot. But you see here, this is what's setting it. Or maybe you say, forget it, I'm going to go all the way to Inconel. I'll make the entire skin, Inconel skin, can handle 1700 Fahrenheit. And maybe it's worth it because at Mach 4, you get up to 400. Or Mach 5, maybe you're able to finally push it up to that speed. Maybe you can handle then 300 pounds per square foot. But this is ultimately what is going to drive that choice. And so this is normally why when people say hypersonics are hot, well, yeah, they are. It's because of this. Or they say hypersonics requires new materials. Well, it can if you need a temperature more than these, right? If you're trying to fly, at thicker atmosphere, say, because you're a weapon, then yeah, you're going to quickly be well past these dynamic pressures and well past these temperatures. Okay, so that's the temperature portion, right? And then we're going to get into a few other things. I'm going to come back to this kind of black screen. Right? A few more things on this. This was just looking at the skin friction. We haven't even talked about lift to drag yet. And so I'm going to draw here the it's kind of standard airfoil. You might do a double diamond airfoil. It's not quite symmetrical. Apologies. And you're generating shocks off of this airfoil. Okay, so there's a shock, and you would have an oblique shock here, an oblique shock here. And so you're generating all these shocks off the airfoil. And so normally they're way thinner than this. And that's because in the end, the lift and drag coefficient is going to drive a lot of this vehicle as well. It's going to come into range, and ultimately what angle of attack I'm able to fly at. It's going to be another alpha, which is kind of a pain. It's going to be driven by that. So as these shocks are forming, you can go around and you can look at the pressure distribution. We can actually solve for the pressure behind each one of these shocks, given the flow speed. And so the lift coefficient ends up going like 4 times alpha, angle of attack. And there's the third alpha that you've now seen. That's angle of attack. But you pick up this kind of compression penalty. So if you're flying faster, your lift is actually going down. Right? For the same angle of attack, your lift is going to go down as you go faster. And so this is going to get back to, well, maybe you need a little bit bigger wings, right? In fact, if you said that I've got a vehicle and I don't want to say, fly more than 30 degrees angle of attack, well, I hope you can see that if you're doing that and at Mach 4, this may actually end up completely setting the maximum. Go back to this. There may be some wing loading here you can't go past because you would hit some maximum lift. Like you can't get any more lift out of this. So this becomes important as well. And then just to kind of close in on drag, and this is just the inviscid portion of the drag. There are skin friction drag we talked about over here. This is just the inviscid portion, and this does start picking up a little bit of what we would call wave drag. So alpha squared plus delta squared, delta being that half angle here, and then this also picks up that Mach compression. So the drag is going down as you go faster. That's good. And ultimately, how are these two relating? Well, that's then lift over drag. And I hope you can see here that those terms cancel out. The Mach terms cancel out. And you pick up alpha over alpha squared plus delta squared. And so you can see that the maximum then occurs when alpha is equal to delta. That's actually the maximum, and has a value of 1 over 2 delta. So that's important. I'll circle that, right, or underline that. That means the thinner these get, the better your lift to drag gets. That's important because that's going to drive range. That's going to drive range. So you want really, really thin airfoils. And that's why anytime you've seen a supersonic aircraft, it's always got those really thin airfoils on it. Okay? So that's a key configuration. We've got friction that's driving heat. We have also the friction component that's going to show up in drag. We have the lifting, right, our supersonic airfoil. We have some maximum lift that's going to set the maximum wing loading that we have on our vehicle. And then the final piece that we have to look at is then the body drag. So this is the wing. What about the body? So I'm going to draw a very kind of thin looking, almost cigar shape. And this is, it's called the Sears hack. And this is a, body of revolution. We can actually do the math behind this. and know that this is the minimum wave drag behind, the wave drag, and the drag caused by all of these shocks behind this shaped vehicle. And the wave drag on this vehicle is actually 64 times the volume squared over the length to the fourth times rho v squared. Now, I do that important because I've said this a couple of times. I've said that the volume, that the drag of your system goes like the volume squared, and so there it is. That's the term that bites you. And so, way back when we were talking about propellant density, that's why this is critically important. Or when you think through the early generations of rocket-based combined cycle, where we know this works, but gosh, the mixing length required, the duct length required for that rocket plume to mix with the air to then drive a ramjet is a really long time, so it took up a lot of volume. That's really where that started being a penalty. And then what is kind of nice with this, and you can convert this to a drag coefficient if you want by pulling off the dynamic pressure, but there's a thing called area rule. Area rule. Gosh. Let's say I wrote area. I'll know I wrote area. Where you can actually take a look at this, that if your vehicle can start approaching the shape, that will be minimum drag. And we've actually seen that in a couple of different designs that we've, us humans have already designed and flown and shaped. And if we can kind of pull down at the global level to make it smooth, we do see an improvement in supersonic flight. So that's an important configuration as well, because we don't fly cigars, we don't fly two-dimensional airfoils. We'll fly this combination of them. And so you can work through the area rule, and it's a decent first approximation to help drive what your design shape starts looking like. Okay, so with this, then we've now kind of got an idea behind the altitudes that we can fly at. Right, I showed you those temperature curves. We started talking about the maximum lift you're going to actually be able to generate given a certain angle of attack that you're happy with. 30 degrees might be pretty bold. We know we want the wings thin, and then we know that we want kind of long, slender things, and that any volume, any inefficiencies in volume is really going to start hurting. And so all of those considerations start pulling in. And then the last one on here, we'll talk about the weight on the next little episode, but the last one is alpha. And so we know that on rocket-based combined cycle with our detonation engine, we're going to have a curve for alpha that does something like this. And I've already got baked in here the flight profile based on the temperature that we're going to fly. And so, we'll have some takeoff alpha. We'll actually get more as we get high enough that we can light the ramjet. And so that our alpha will go up for a little while and then come back down. And so when we're talking about, say, a cruise alpha, it will be using more of, say like 0.25, something like that in the cruise alpha. And then just to kind of complete it, if we looked at ISP versus Mach, again, kind of drawing roughly what that rocket-based combined cycle is doing. We have sort of some mixing, we then pull up, and then this is the standard 1/V sort of ramjet curve that we then chase to. And again, as a reminder, turbine-based combined cycle would be sort of here and then down. And so the benefit behind rocket-based combined cycle, we do pay for the ascent with a little bit more propellant usage, but then we achieve the same ramjet condition, and in the end, we get rid of the weight of the turbine. We also get rid of the volume of the turbine, which becomes critically important. So I've now shown you the volume part and why we would rather pay for fuel. Fuel is more dense than that turbine that you're dragging along with you. So next episode, we'll then dig into a few more things on the weight side, and then we'll be ready to complete and look at our mission. See you then.